Okay, welcome to another video. And what we're going to be looking at in this video is some of the nice forms that matrices can be in, and kind of how do we tell between kind of when a matrix is in a good form and when it's not. And so these two forms are called row echelon form that we're going to look at, and reduced row echelon form, which are kind of funky words. But I'll kind of explain what that means as we go along here. Okay, so what I have here, I have three matrices over here, and each one is kind of in a different form. And to tell what form one is in, what you want to do is you want to identify the leading terms. So leading terms are the ones that, like the first non-zero term in a row or column. Okay, so like if I look in this row here, the leading term in this row, well, it's the first non-zero thing, so it's this one right here, this one, okay? So that's the leading term of this row. Now, the leading term of this row is this guy right here, okay? And then the leading term of this third row, or sorry, this one right here is this number one. It's the first non-zero thing in, and then this one, it's this one, okay? Now you'll notice here there isn't really a good pattern with what's going on here. The leading term starts here and then goes here and then jumps to here and then jumps to here. We really don't like it when it does that. We don't like matrices when they're in that form. So this is none of the forms, okay? Generally what we like to have happen for a matrix is we like to start with a leading term over here and then have our leading terms kind of move to the left and down as we do it, okay? So I'll kind of show that on this next one. The leading term of this first row is right here. It's this one. The leading term of the second row is right here, okay? The leading term of the third row is here, okay? And then there isn't a leading term on the last row, okay? But you'll notice here there's kind of this stair-step pattern of to get to the next leading term down, we're going to the right, okay? And to get to the next leading term, we're going to the right. We like to have it in kind of a descending pattern here, a descending kind of path of leading terms, okay? So now that's not the only thing we want to have happen for these nice forms, okay? But this matrix here, this is an example of something that's in what's called row echelon. If I can remember how to spell it. Row echelon form. Okay. Row echelon form. And basically that says that, well, our leading terms, the leading terms all need to be 1, and they need to be in this descending pattern, okay? So these are all 1. All my leading terms are 1. And they're in this descending pattern, and then there's zeros underneath, okay? So notice anywhere there's a leading term, there are zeros below it. So there's zeros here below this leading term. The other leading term, we've got zeros right here. And then the other leading term, the last leading term, we've got zeros right there, okay? And so that will make it in what we call row echelon form, okay? And I'll show you why we care about this form so much, especially In the next video, I'm going to show you how you solve systems of equations once you have the matrix in this form. But it turns out it's a really nice form when you're trying to solve equations. If you end up with this, you basically have your answer. You don't have to do too much more. So that's why we care about it. What's even better than row echelon form, okay, we like this way better than row echelon form, because this will actually give you your answers all the time, is what we call reduced row echelon form. And this third matrix here is an example of it. Reduced row echelon form. Okay, so that's an example of it. And let's look at what is going on in this matrix. So let's first determine the leading terms of this matrix, okay? So on this row, the first non-zero term is right here, it's 1. Then the first non-zero term on this row is here, it's positive 1. The first non-zero term here is 1, okay? So those are my leading terms. They're all 1. And notice below those leading terms, okay, we've got zeros here, here, and here, okay? So you'll note that this is in row echelon form because we've got our descending leading terms and there's zeros below those leading terms, okay? But what makes the reduced row echelon form different is that above those leading terms, you also need to have zeros, okay? So there needs to be zeros up here too, okay? So for a reduced row echelon form, you have descending leading terms and then zeros above and below those leading terms. And I'll write this out in a second as well, okay? But why do I care about this so much, okay? Why? I want to first kind of motivate, why would I care about these forms? Well, I'm going to focus on just the reduced row echelon form for a minute, okay? If this was an augmented matrix here, okay? We'll say that this represented a system of equations. Well, let's translate that back into equations, okay? So this first column here would correspond to my first variables. Those would be the coefficients in front of x. These would be the coefficients in front of y. These would be the coefficients in front of z, this column. And then this last column would be a fourth variable. Maybe we'll call w, okay? For a system of equations, right, the columns refer to the variables, the coefficients of the variables. So what would this look like in terms of a system of equations? Well, I'd have 1x, so just x, and then plus 3y, and then there's 0z and 0w equals 0. Okay? Now, on this other one, I would have 0x, 0y, and 1z. So in other words, just 1z, and then 0w, and that would be equal to -3. Okay, because our last column is always just the numbers that were on the other side. Well, that's a really nice equation we have here, okay? We know what z is already, okay? And then our third row here is 0x plus 0y plus 0z plus 1w. So 1w is equal to 1/2, okay? So, and then this last equation is 0x plus 0w plus 0z plus 0w is 0. So in other words, 0 equals 0 is that last equation, essentially. So it doesn't really matter because it That's just true, okay? That's always true. But when you look at this system of equations right here, this is a really simple system, right? You've got z alone, you've got w alone, right? The only thing you don't have alone are x and y, which it looks like you can do any combination of x and y that satisfy this equation because there's no other conditions on x and y. So on this, there's infinitely many solutions, okay? But this is really nice because this is a very simple form. Like this matrix gives us a really simple system of equations, okay? I'm going to look at just one more example of this and show you just kind of why we care about this so much. I'm going to move this. Okay. I'm going to draw another matrix. Let's say that I have a really nice matrix, which I'm sure we're going to see a whole bunch as we do this. Okay. And then 0, 0, 1. Okay. And I'll just say 2, 3, 4, 5. And sorry, that line there is just to help you keep track of which ones are the answers and which ones are the variables. But generally in our book, we don't have that. So I'll erase that for you. So what does this say? Well, first of all, is this in reduced row echelon form? Well, here's leading terms, right? Those are my leading terms, the first non-zero things on each row, okay? Below them, there's zeros, okay? And above them, there's zeros, okay? And so this is reduced row echelon form. And what happens when I convert this into equations? Well, this first column is x, the coefficients of x. The second column is the coefficients of y. The third column is the coefficients of z. And then the fourth column is the fourth variable. Maybe we'll call it w. Okay? So what would I get? I would get 1x. So 1 times x is just x. 0y is 0. Okay, so plus 0y is 0. And then plus 0z is 0. Okay, plus 0w is 0. Okay, and that would equal 2. Oh my. Okay, that's pretty nice. We like that. Y on the second row, right? 0x, well that's 0. 1y, got 1y. And then 0z, 0w is 3. Oh my, that's real nice. Okay, and then z, well, 0x plus 0y plus 1z plus 0w is 4. Okay, so I'm just taking the rows of this matrix and interpreting them as equations. And we see that when we do this, we get a really nice equation out. In fact, this last one is 0x plus 0y plus 0z plus 1w. So 1w is equal to 5. Okay, so this is really nice because when it is like this, it tells us what our solutions are. Okay. So that's why we care about these forms. I think that's it for this video. Before I finish, I will write out just kind of a description of what these forms are formally so that you can kind of keep track of that. Hopefully that will be helpful. Let me pull up another one here. Okay, so just to review, there were two main forms of matrices. There was row echelon form. Okay, and what it has is that leading terms are all 1. okay? And leading terms go to the right as you go down. Okay, so as you go further down the matrix, the leading terms should go to the right. In other words, it's kind of a descending chain. Okay, and then the book does have a last condition that rows of all zeros are at the bottom. Okay, now this isn't a super important rule, but it is something the book has on there. Okay, so now let's look at reduced row echelon form. Reduced row echelon form. Well, it's basically the same as row echelon form, so it has all the same conditions. It's just there's one extra one, okay? And that is, oh, sorry, I missed one up here, okay? Let's start over. Okay, sorry, I missed one here. We needed to have zeros below leading terms. Okay, so that was all the conditions you needed. Sorry, this one was something I didn't mention. It's not something you run into too often. Mostly it's this. You need to have the zeros below the leading terms. Okay, so, sorry, reduced row echelon. Oop, that's not spelled right. Echelon. Form. It's basically the same as row echelon form. It's just there's an additional condition, is that there needs to be zeros above the leading terms. Okay. So, as well as below. Okay. So, any reduced row echelon form is going to be a row echelon form. Okay. But not all row echelon forms will be reduced. Okay. Normally we like the reduced row echelon form more than the row echelon form because you can, the equations are a lot simpler for reduced row echelon form. In fact, they're as simple as you can go. But row echelon form is simpler than just the system to start with. And in the next video, you'll see kind of how row echelon form can be powerful in solving equations as well. And soon you'll get to see how we are going to transform equations so that they fit these forms. Okay?